My name is Dr. Paul Bilokon, and I have been a quant for more than 2 decades, and I'm also a visiting professor at Imperial College London. So today we'll talk about differential machine learning for Heston calibration. These slides are based on my joint work with Sridi, and you can find a preprint on this work on SSRN. If you Google for my name and SSRN, you will find my SSRN page, and you can find the original paper there. So we'll walk you through the practitioner's pipeline. We'll go through the Heston pricer that returns normalized forward-put prices and their sensitivity. And then we'll, after that, look at the twin or differential neural network that learns prices and their differentials. And it learns them jointly. And finally, we'll look at the online calibration procedure that uses the trained network as a millisecond pricer, very fast pricer. So so these ideas originate from our work with Sridi, and they're focused tightly on what desk quants and developers actually need. And that's speed, robustness, and reproducibility in daily production calibration. I'll highlight implementation decisions and pitfalls that we found important in practice, as well as recommended results, recommended defaults that you can use in a production environment. Now, if you want to follow along later, the slides and code snippets will be based on the material that I have provided, so feel free to ask for these slides afterwards. And there will be a basically what did I want to say? Perhaps I wanted to say that this work originates in the deep volatility tradition that was developed by Blanca Hall and her colleagues. So this is very much done in the tradition of deep volatility or deep learning volatility, and also this is following the work in differential machine learning by Savine and Hugh from Danske Bank itself. So it follows these two traditions, and it follows these two strands of thought that are incorporated into our reasoning. I guess the next thing to address is really who are these slides for? Who are these slides for? They're for desk quants and developers. But these are basically three overlapping groups. The first group is desk quants and developers who want to deliver fast and robust Heston calibration in daily production. People who need a substitution pricer that is both accurate and fast. The second group is the risk and model validation teams who are interested in deterministic noise-free objective functions for calibration. And that's precisely what differential machine learning, what DML produces. It produces smooth objective landscapes via differentials, which is very attractive to model validation professionals. And finally, we're looking at researchers who want to benchmark differential machine learning against classical deep learning baselines. Okay? So if you identify with any of these three groups, the methods we discuss are directly relevant. My approach is very pragmatic. There are no exotic model architectures, just reliable, straightforward, reliable neural networks and careful data design that give big wins in generalization and calibration speed. So if you follow these slides, maybe before we continue, let me just very quickly tell you, when I was first asked to deliver a daily calibration process for a front office desk, the metric was really blunt: don't let trading stop. Okay, so that meant sub-second hedging decisions had to be backed by a pricer we could trust, right? So that's the pressure that shaped the practical decisions I'll show you today, especially around sampling, numerical checks, and risk controls. So here is what you will build if you follow these slides carefully, and what I'll guide you through three tangible deliverables that you can implement after this talk or during this talk. Basically, puts on hold and start coding as we speak. The first one is a Heston vanilla pricer that returns normalized put prices and, crucially, their sensitivities, depriced by the input. Producing analytical semi-closed sensitivities is central to training the twin network. The number two is this twin or differential network that learns prices and differentials jointly. The twin architecture is the heart of DML, differential machine learning. The network outputs both the scale price and its gradient with respect to inputs. And the third deliverable is an online calibration routine that treats the trained network as a millisecond pricer. The network replaces slow semi-analytical pricing during calibration, enabling fast, robust parameter search in production. Throughout, I'll emphasize practical choices, sampling ranges, activation functions, normalization, and the loss function design that materially affect performance. And by the end of the talk, you'll have a clear plan for three deliverables: a Heston pricer that returns normalized forward put price and sensitivities, a twin neural network that learns values and gradients, and an online calibration routine that treats the network as a millisecond. And I'll basically show you some code skeletons. I'll talk about training defaults and pitfalls to avoid. So before we go further, why gradients? Well, because calibration is an optimization problem, and good gradients are the difference between a smooth objective and a noisy, unpredictable one. So let's recall the Heston model. Let's look at these equations briefly to set the notation. So the spot follows this process, and then there is also the variance process, and there is a correlation between DW1 and DW2. That's the correlation. We basically use the general standard Gatherall-Taleb stable characteristic function combined with Lipton-Lewis one integral formula for efficient semi-closed pricing. And the reason for this choice is practical. Right, the one integral formula is numerically efficient and differentiable and allows us to compute prices and semi-closed expressions for sensitivities, which we'll use as labels for DML training. And as a reminder, while the Heston SDEs are familiar, the details of the characteristic function, integration contour, and numerical truncation matter for stability and for making the sensitivity computations robust. Once on the desk, I know, a subtle change in integration truncation created spurious oscillations in Greeks overnight. The hedging P&L briefly looked like markets panic because the prices started returning noisy deltas for short maturities. That was a costly wake-up call. Robust, well-tested integration is not a luxury, it's a requirement. So be aware of those pitfalls. So now, let's look at the normalized forward put price. Right, normalized forward put price. For calibration and learning, we use this normalized forward put price to keep labels numerically stable across moneyness and maturities. The normalized forward put price is defined by the call put parity and the integral over the characteristic function. There we go. There are two practical points here. First, by working with normalized forward, we get labels in a tighter, more stable numerical range, which is ideal for regression. And the second practical point is that this quantity admits semi-closed differentials with respect to all model inputs we care about, which are, of course, theta, kappa, sigma, rho, v0, m, r, and tau. That's the gateway that lets us compute target gradients efficiently for the differential loss. Now, of course, we look at Black-Scholes as a special case. We recover Black-Scholes. It's quite helpful to see Heston in relation to Black-Scholes in a limiting regime. And this provides intuition about label behavior. Because for small sigma and for theta approaching V0, the model's implied variance tends to the Black-Scholes variance. Okay? And in the limit, as sigma tends to 0 and as when theta is equal to V0, sigma Black-Scholes is going to be the square root of V0. And this tells us that for some parameter settings, Heston reduces to behavior close to Black-Scholes, meaning the labels and gradients will reflect that limit. When generating training data, we should ensure that the sampling captures both stochastic vol regimes and near Black-Scholes regimes. Otherwise, our model may extrapolate poorly near those edges. Once a junior quant complained that the surrogate didn't learn Black-Scholes, and we traced it to the training box. Regions where sigma is close to zero were missing. After adding those samples, the network's behavior on near Black-Scholes settings became flawless. Simple sampling mistakes do bite in production, so be aware of that. So we have this two-step DL and versus DML. What's that? It's an important conceptual comparison. Two classic two-step deep learning, the classic deep learning approach, two-step deep learning approach is quite straightforward. First, you train a neural network. FW, there we go, to map parameters, there they are, to normalized put forward price, P hat, on synthetic data. And then we use, as a second step, during online calibration, we optimize the parameter vector, this parameter vector. We have this kind of fancy theta for it here, to minimize the squared error between network predictions and market prices. Whereas the differential machine learning approach augments the labels with differentials. Okay, augments the labels with differentials. We don't just regress price. We also regress price gradients. And that's formally the loss is this, right? Where the second term over here, penalizes deviation of network gradients from ground truth gradients, and the lambda over here controls the weight of the differential penalty. Intuitively, training in differentials regularizes the function class. The network class is encouraged not only to fit values, but also to respect the local derivative structure of the true pricer. This yields smoother and more physically consistent approximations, which improves generalization dramatically, especially in low data regimes. Now, in practice, what does the twin network look like in practice? The architecture is conceptually simple, but with an important twist. The forward half is a standard feed-forward neural network using soft plus activations, which is smooth and positive, which is useful because price outputs should behave smoothly, and we want differentiable activations for stable gradient computation. Whereas the backward half shares the same weights but uses the derivative of the forward activation. Effectively, the backward activations are the activation's derivatives. For example, soft plus's derivative is sigmoid. This twin structure enables the model to output price values, while the backward half naturally yields the gradient structure. Here is a critical implementation point. We must use smooth activations to ensure the twin network is differentiable everywhere. Non-smooth activations, like ReLU, break the requirement and lead to noisy gradients. So choose soft plus, tanch, or other smooth activations when implementing twin networks. In one experiment, we used ReLU because it was fast, and during validation, the calibration jumped around depending on which sample the ReLU functions hit. We switched to soft plus, and the objective became monotonic. Here's a lesson. Fast at the activation level can cost stability at the system level. Now, data generation. Synthetic data generation. Data generation is probably the single most important practical step. We used Latin hypercube sampling across sensible parameter ranges so that the training set covers the parameter box efficiently without clustering. These are the ranges that we used, and for each sample point, We compute both the price and the differentials from semi-closed formula. After generation, we normalize inputs and labels and scale the differential. And that means that we divide gradients by input and label standard deviation so that the loss terms are numerically balanced. Here are a few practical tips. Enforce the Feller condition during sampling to reduce degeneracy near zero variance, and avoid sampling parameters that make the characteristic function numerics unstable. Finally, keep a holdout test and validation split. A typical split we used was 80-10-10. Generating labels can be expensive. At one bank, synthetic label generation for 100,000 samples took a cluster overnight, and the desk wanted the results the same morning. The solution was pragmatic. We started with a smaller DML set, about 16,000, which provided excellent generalization, and then produced larger batches overnight for robustness checks. Here is the moral. DML often lets you get away with far fewer labels than classical DL, and that saves significant compute and time. Okay, so network and training defaults. These are the defaults that worked well in our experiments and are a sensible starting point for production trials. We have 4 hidden layers, 50 neurons each. We have forward activations, soft plus, backward, sigmoid for the twin structure, and the head is linear, predicting the normalized forward price. The optimizer is Atom W with adaptive learning rate. Adaptive learning rate schedule is usually a good choice. The decoupled weight decay in Atom W acts as a clean level L2 regularizer. And then we have the training regime. 50 epochs, 16 batches per epoch, and a batch size of 819. Initialization, k-ming for weights, and uniform for biases, and that worked stably. In terms of data set size, the differential ML performs strongly even for modest data sets. We found that DML works well with as few as 16,384 samples, a much smaller requirement than classical DL baselines to reach comparable generalization. We tune these against validation MSC and gradient MSC. We monitor both. And I think let's look at the performance snapshot. This slide summarizes the core empirical result. DML substantially improves generalization. On test mean squared error expressed in basis points, a simple sequential model scored around 6.29 BPS. A classical fully connected neural network around 2.6 BPS, and the DML twin network about 0.44. That's an order of magnitude improvement over classical DL. 2 further practical lessons. Enforce the Feller condition during generation. This reduces degeneracy near zero variance and improves stability. The second one, DML with 16,000 samples outperformed classical DL with 100,000 samples. In production, this reduces data generation cost and speed experimentation. Empirically, DML improved test MSE dramatically versus classical baseline. So, yes, it was an order of magnitude better. This drop in data need, and also we performed at 16,000 as opposed to 100,000, and this drop in data need matters in the trading world where label generation has a CPU cost. One desk reallocated overnight compute from brute force label generation to faster hyperparameter sweeps because DML reduced the label requirement. Operationally, that changed priorities. More models were trained per week, and calibration robustness improved faster than expected. So let's talk about regularization. Regularization in DML has a few moving parts. First, Atom W with decoupled weight decay provides implicit L2 regularization. It worked nicely in practice. Second, conventional techniques like dropout and early stopping remain useful. We recommend them if you suspect overfitting. Crucially, the differential penalty lambda is itself a powerful regularizer. It constrains the function's local behavior and prevents weird oscillations the network might otherwise use to fit noise. Normalization is essential. Z-score inputs and labels over here. Scale differentials by input standard deviation to label standard deviation, so the gradient loss term has the right magnitude relative to the value loss. If you don't scale differentials properly, the optimizer will either ignore them or be dominated by them. Regularization is twofold: conventional Adam W, weight decay, early stopping, dropout, and the differential penalty, lambda, which acts as a structural regularizer. Correct scaling of grads, dividing by input STD, output STD, is necessary. If you get the scaling wrong, optimizer either ignores gradients or is overwhelmed, as I said. I once saw a model train where the gradient loss completely dominated due to a missing scaling factor. The price MSE was terrible, despite a tiny gradient MSE. We spent a day debugging until we discovered a unit mismatch in the grad labels. Always sanity check units and scaling. Now, here is the PyTorch skeleton. It's a compact PyTorch skeleton for the twin network. The main piece is a twin FFNN module that builds a forward net using soft plus activations and a linear head for price. The method price and grads makes X require gradients and computes the output and gradients using torch autograd.grad. A few implementation details to note. First of all, ensure that X requires grad true before forward pass so autograd can collect gradients. When computing gradients for many samples in a batch, use the y.sum in autograd.grad to compute the per sample gradient with respect to inputs properly, or compute Jacobians carefully if you prefer per sample vectorized derivatives. Avoid create graph equals true unless you need higher order derivatives because it is expensive. And this skeleton is intentionally compact. Production code should add checks, device handling, logging, and stable numerical strategies for gradient calculation. Also watch your memory footprint when computing gradients for large datasets. In production, we had to disable AutoCast for the final gradient computation because it introduced an infinitesimal bias in some Greeks that our risk team noticed. For everything else, we happily used mixed precision to speed training, but keep the sensitive gradient computations in full precision. So, this is our training loop with value and differential labels. It's straightforward conceptually. For each batch, we load XB, YB, and DB, where DB are the differential labels. We compute Y hat and D hat from the model, compute the mean squared error for prices, and a scaled mean squared error for gradients, and the overall loss over here is going to be equal to the loss underscore val plus lam times the loss diff. So, some practical tips. Scale differentials by per feature norms if desired, so that a gradient discrepancy in one input dimension does not dominate the loss. Monitor both components for the loss separately in logs. Sometimes the value loss decreases with the gradient loss, while the gradient loss stalls, indicating learning imbalance. If the gradient loss dominates early in training, consider a warm start phase where lambda is small, and then gradually increase it. A curriculum can help optimization. Now, keep an eye on learning rates. Differential losses can be more sensitive to steps and benefit from adaptive schedules. We found that a small lambda initially, say 0.01, that linearly increases to 1 over the first 10 epochs, helps optimization stability. The warm start is cheap and stabilizes convergence in many cases. So, once you have a trained twin network, you can use it as a millisecond pricer inside an online calibration routine. Because the network is quick to evaluate and produces cheap gradients, you can embed it in many optimization schemes. Here's a straightforward approach we used in differential evolution that minimizes calibration objective built with network predictions. In code, differential evolution with the calibration objective and parameter. Because the network is deterministic and smooth, stochastic optimizers converge reliably and the objective surface is less noisy than one built from Monte Carlo estimates. There are two obvious calibration improvements using DML. You can compute Jacobians of the objective cheaply via chain rule combining network gradients and price mapping, enabling gradient-based optimization, or you can use global optimizers like differential evolution as a robust fallback. Both are viable in production depending on latency and robustness needs. Once the twin network is trained, it becomes a millisecond pricer for online calibration. In a production rollout, we swapped the desk's semi-analytical pricer for a DML surrogate inside a calibration loop. Latency dropped from 120 millis per evaluation to 3 millis. That allowed the desk to run an additional hedging recalibration every 5 minutes instead of every hour, and that materially reduced intraday exposure during volatile windows. Always keep a fallback. If the surrogate is asked to extrapolate, you should detect it and revert to the trusted slow pricer. So, some checks and pitfalls. Numerics. When you compute the semi-closed intervals, use SciPy integrate quad-vec with vectorization and sensible truncation bounds. Poor numeric truncation yields label noise, which kills gradient supervision. Feller. Generate training data under the Feller condition to reduce degeneracy near VT equals 0. If you sample aggressively without this check, you'll get pathological samples that hurt learning. Box discipline. Do not extrapolate the neural network outside the trained parameter ranges. Neural nets are notorious for producing nonsensical outputs when asked to extrapolate. If you need coverage beyond your initial box, expand the sampling box and retrain. Scaling and reporting. Always denormalize outputs when reporting errors in basis. Training losses can be misleading if you forget to undo the dead scoring before interpreting performance. Operationally, build health checks, unit tests for integrals, distributional tests for gradients, and an out-of-the-box detector that refuses to use surrogate outputs if input norms are outside training support. Here is a classic ops story. A desk pushed the surrogate live without an out-of-box detector. Overnight, a market with extreme skew fed inputs outside the training domain. The surrogate produced nonsense valuations for deep short-dated tails, and automated hedges went wrong. The fire drill that followed cost time and credibility. We rebuilt the process with an automatic revert and strict monitoring, and we never run in production without them. And here are the suggested defaults. To help you bootstrap experiments quickly, these are some working defaults. These are not ironclad rules. They are a robust starting point. You'll find some hyperparameters sensitive to particular markets or instruments, so treat these defaults as a scaffold for fine-tuning. When you hand these defaults to a new team, expect them to treat them as gospel. They are not. Use them as a starting point. Log experiments and keep a lightweight hyperparameter sweep. We run quick grit sweeps on learning rate and lambda once per model. Now, this iterative approach beat chasing bespoke magic for months. Now, to summarize, the main takeaways are: differential machine learning, training on both price and gradients, substantially improves generalization versus classical deep learning and does so with less synthetic data. Twin networks require smooth activations like soft plus and use shared weights to model values and derivatives consistently. A trained neural network serves as a fast, stable millisecond pricer, enabling quick online calibration either via global optimizers or gradient-based routines. Practically, careful data generation, correct scaling of differential labels, enforcement of Feller during sampling, and attention to numerical integration are all essential to success. If you take one particular point away from this talk, incorporate gradient information into training. It's a disciplined way to inject model structure into the learning process, and it yields better, more realistic surrogates. So, I would like to thank Abir Sridi for her help in preparing this material, and I will give you some discussion points that you can use. Think about what type of surrogate prices you have used, if you've used them. What are your latency and robustness targets? And think about how you can integrate DML into the existing pricing pipeline. I hope you've enjoyed this talk. Thank you very much.